Hello viewers. Welcome to the YouTube channel. In this video we will discuss Class 12 or 2nd PUC Physics Chapter 2, that is Electrostatic Potential and Capacitance. Class 7. From basic to advanced level, for board, JEE, KCET, and NET. Do support watch till end, don't forget to comment, share, subscribe the channel. In previous class, we studied capacitor and capacitance of parallel plate capacitor in presence and absence of dielectric medium. That video link is given in description, don't miss it. Today, we discuss combination of capacitor and their derivations. Let's start. Define dielectric constant. Dielectric constant is the ratio of capacitance of capacitor when space between the plates is filled with dielectric to the capacitance of same capacitor when space between the plates is vacuum. Next, equivalent capacitor and equivalent capacitance, effective capacitance. A single capacitor which produces same effect as that of set of capacitor is called equivalent capacitor. And its capacitance is called equivalent capacitance. Now we will see combination of capacitor. There are two combination. 1. Series combination. 2. Parallel combination. Let's study one by one. Series combination. A set of capacitors is said to be in series if they are connected end to end such that 1. The potential difference across the combination is equal to the sum of the potential differences across each capacitor. 2. The charge on each capacitor remains same. Let's derive an expression for effective capacitance of a series combination. From above figure, A and B are two capacitors connected in series. C1 and C2 are the capacitance of A and B respectively. V1 and V2 are the potential difference across A and B respectively. V is the potential difference applied across the combination. Let Q be the charge on each capacitor. Cas be effective capacitance of series. In series combination, total potential across the combination given by V is equal to V1 plus V2. Mark as equation 1. We have V1 is equal to Q by C1. V2 is equal to Q by C2. From 1, V is equal to Q by C1 plus Q by C2. On taking Q common, we get V is equal to Q into bracket 1 by C1 plus 1 by C2. Mark as equation 2. But, for effective capacitance of series, V is equal to Q by Cs. Substitute in equation 2, we get Q by Cs is equal to Q into bracket 1 by C1 plus 1 by C2. On cancelling Q both side we get 1 by Cs is equal to 1 by C1 plus 1 by C2. This is the expression for effective capacitance of two capacitors in series. For n capacitors in series is given by V is equal to V1 plus V2 plus V3 plus up to Vn. Therefore, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 up to 1 by Cn. This is the expression for effective capacitance of n capacitors in series. Next is parallel combination. A set of capacitors is said to be in parallel when they are connected between two common points such that 1. The potential difference across each capacitor is same as that applied across the combination. 2. The total charge stored in the combination is equal to the sum of the charges on each capacitor. Let's derive an expression for effective capacitance of a parallel combination. From figure, let A and B are two capacitors connected in parallel. C1 and C2 are the capacitance of A and B respectively. Q is total charge of combination. Q1 and Q2 are the charge on C1 and C2 respectively. V is the potential difference applied across the combination. Cp is effective capacitance of parallel. Potential difference across A is equal to potential difference across B. Therefore, in parallel combination, total potential across the combination given by Q is equal to Q1 plus Q2. Mark as equation 1. But we have Q1 is equal to C1V and Q2 is equal to C2V. From equation 1, substitute the values in equation 1, we get Q is equal to C1V plus C2V. Take V common. Then Q is equal to V into bracket C1 plus C2. Mark as equation 2. But, if the combination is replaced by equivalent capacitor Cp is Q is equal to Cpv. On substituting above equation in 2, we get Cpv is equal to V into bracket C1 plus C2. Cancel V on both sides. Cp is equal to C1 plus C2. This is the expression for effective capacitance of two capacitors in parallel. For n capacitors, Cp is equal to C1 plus C2 plus C3 plus C4 plus up to Cn. Note 1. In series combination, charge on each capacitor remains constant. 2. In parallel combination, potential difference across each capacitor remains constant. 3. If C1 and C2 connected in series, then 1 by Cs is equal to 1 by C1 plus 1 by C2. Just cross multiply C1 C2 we get C2 plus C1 by C1 C2. Therefore, Cs is equal to C1 C2 by C1 plus C2. 4. For n capacitor in series, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 up to 1 by Cn. For n identical capacitors, C1 is equal to C2 is equal to C3 is equal to up to Cn is equal to C. Therefore, 1 by Cs is equal to n into 1 by C. That is, Cs is equal to C by n. 5. If n identical capacitor are connected in parallel, Cp is equal to C1 plus C2 plus C3 plus up to Cn. Therefore, Cp is equal to n into C. Next, derive an expression for energy stored in a capacitor. Let plus Q and minus Q be charge on conductor 1 and 2 respectively. V1 and V2 be the potential of conductor 1 and 2 respectively. E be the electric field. Consider a capacitor which is initially uncharged. When a battery is connected across the capacitor, the charge transfer from one plate to another plate as shown in figure, as bit by bit in small amount dq from 0 to q. Consider an intermediate situation when the charges on the plates q and minus q. At this stage the potential difference between the plate is. Therefore, potential difference V dash is equal to Q by C. Mark as equation 1. Here, dq is a small charge is transferred from conductor 2 to 1. dw is small work done to transfer dq. But dw is equal to v dash into dq. Mark as equation 2. Therefore, dw is equal to q by c into dq. Mark as equation 3. Total work done to transfer a charge from 0 to q is w is equal to integration from 2q into dw. Mark as equation 4. From equation 3 in 4 we get w is equal to integration from 0 to q into q by c into dq. Therefore, on taking 1 by c common, we get w is equal to 1 by c, integration from 2q into q dq. For integration of q dq can be solved from this formula. That is, integration of x to the power n into dx is equal to x to the power n plus 1 by n plus 1. Here n is equal to 1. So, we can write as w is equal to 1 by c into q to the power 1 plus 1 by 1 plus 1 from 0 to q. That can be written as w is equal to 1 by c into q to the power 2 by 2 from 0 to q. On taking 1 outside, w is equal to 1 by 2c into q square minus 0. Finally we get w is equal to q square by 2c. Work done is stored as a potential energy. Here, work done is equal to potential energy. W is equal to U. Therefore, U is equal to q square by 2c. This is the expression for energy stored. Here some other forms of expression is 1. U is equal to 1 by 2cv square. 2. U is equal to 1 by 2qv. Here ends the chapter 2. So don't forget to subscribe the channel for more.